Everybody, CUDAN Open Lab Seminar on March, is it 8? 13, sorry. March 13, 2023. And today it is our greatest pleasure to have Eduardo Altmann joining us from Australia live at 1 p.m. Tallinn time. And Eduardo will talk about complex systems approaches to social data, which is a topic that is very close to my heart. Complexity is something that is everywhere in sociocultural systems, and it's also something that is hard to get funded in general, and particularly hard to get funded to study social cultural, or even more so cultural complexity in cultural products. And so today we're going to learn something about that, and also, as I'm semi-familiar with Eduardo's work, I think we get some really foundational kind of input regarding complexity also. So I'm very much looking forward to that. We will operate, as Eduardo just said, in 2 blocks, and he will take questions along the way. And so with that, Eduardo, the stage is yours, so you can introduce yourself if you like, or just take it away with your topic from where you are.
Thank you, Maximilian. Thank you for the invitation. Let's see if I can share my screen well. Yeah. Okay. Can you see my presentation now?
Yes.
Is it
awesome? Great.
Yeah. Okay. Good. So. Yes, it's really a pleasure to talk to such an interdisciplinary audience, and always a challenge as well. So I myself am a physicist by training from statistical physics. I'm now in a applied mathematics department. I'm interested in working in networks, computational social science, data science. But today I will put my head as a complex systems scientist, right? So we'll try to approach this analysis from this field of complex systems that I think is a very broad and inclusive field. And we'll try to discuss critically what can we contribute to these areas of analyzing social data, social problems in social sciences, and why we haven't contributed as much as I think we could have. I think that is how I'm. So we have a manageable number of people in the audience here. So maybe I will ask, how many of you identify yourselves as someone working in complex systems, or how much of your research, or is there a substantial part of your research that you would consider as part of complex systems? Can I get a feedback? Yeah, there are these buttons now in Zoom, right? So thumbs up, thumbs down. Yeah. Oh, okay. Yeah. Maybe no. Okay. Thank you.
Don't be shy.
Valid answer as well. I see the majority is a yes, but there are no's, right? So, and if we try to, I think there is no need to argue here that there is a vast amount of new data sources. Part of them are available for investigation, and also the view that these data sets can be used to do science in a broad sense, to understand things, and not only in a commercial setting. And if we look in terms of some keywords reflecting some scientific disciplines or terms, areas, we can see a dramatic growth in what is now sometimes called data science, and we in the last decades, scale of a decade, and we don't see this inflection point, right? So in keywords associated as to complex systems or complex system science, like complex networks or complexity science. No? So that is my motivating questions are then, why don't we see a larger impact of the growth of this availability of data in the field of complex systems, and how can these fields, the ideas of these fields, contribute to data science? So that is my driving questions here in general. I mean, one obvious answer is that the dominating tools and methods being applied are coming from this field that we call machine learning. That is even responsible now for the rebirth of artificial intelligence, a much older term, and also there are other older fields like digital humanities that are also not showing the same inflection or the same growth of these other areas, right? So one of the reasons is that certainly the dominating tools and approaches to the analysis of these data sets are coming from machine learning, a subfield of computer science that focus on methods, right? So machine learning is devoted to understanding and building methods, right? So generally applicable methods, right? So it's a subfield of computer science, and any definition you wish will be giving different flavors of these ideas, right? So, and I think it's an interesting discussion from Hannah Wallach already a few years ago about this interdisciplinary, transdisciplinary relationship happening in many of the social sciences, and also the difficulty sometimes of understanding each other, right? So, and she was listing that social sciences will study social things. It is a question-driven science. It's traditionally involving small design data and focusing on explanations. Well, computer science, now which machine learning is a field of, is interested in studying anything. It is methods-driven, as I emphasized, and is looking at large data sets, and the explanations is maybe secondary to prediction, right? So at least in this simplified setting. And I think what we often see, or I often see in my experience, is that there are problems posed in the social science lead to methods in computer science to be used. There is a data that is relevant to a problem. There is an application of these computer science generic methods to this data set, and the output of these data sets, clustering, reduced dimension information, is fed in again to domain experts that will interpret these results. This is often the case in different disciplines. And in fact, this is a relationship that we see also traditionally in statistics. No? So there are the role of statistics in providing tests and analysis for experiments or for data sets observed from specific disciplines. So that is this type of back and forth between the disciplines is not unique here, but I think is very predominant here. And I think in this framework, there is very little space for complex systems approaches. No? What I think is missing here, or what I think another tradition of scientific inquiry that is relevant, that needs to be added here, is what I would now add, motivated by this parallel, what I would call natural sciences. At least the way I see complex systems research is rooted in a great extent in traditions coming from the natural sciences. And I think natural science have a tendency to try to study universal things, right? So the main achievements of the natural science is to explain not only how an apple falls from a tree, but also how the planets move around each other. And if we can explain through a universal theory, that is the most we can aim for. Now, so it is very much model driven, right? So, and if the models work very well, we may call them theory, but it's epistemologically they're models, right? So, and there is a distinction typically between experimental and observational data, which I think is still relevant in the data science world. And the explanations and predictions are often rephrased in terms of validation. Models are validated through experiments, so at least in the physics paradigm. And I think here is where the complex systems tradition can found a resonance, right? So which is complex systems research is very much model driven, right? So it's proposing simple models that show emergent behavior that explain non-trivial macroscopic factors. And that is where the contribution can be, right? So instead of going from problems to methods, I think we need to think in terms of models, right? So models that are able to connect to problems and connect to the methods, right? So mechanistic generative models are clearly connected to the problems, and hopefully we can use them to connect to the methods, to use the methods, right? So, and this is very important, because what is sometimes hidden when we forget about the models is that the methods have underlying assumptions about the generative process of the data. They are often not explicit, but they exist. So, so there is no model-free method, and formalizing the problems and methods in terms of these generative models, we can make these problems and methods more rigorously formulated, both mathematically rigorous, but also with an interpretation. So, and this is then, I think, the point I want to explore is that there is a wealth of complex systems models, and I think as a field we have focused too much in models and forgotten about how to connect them to data. And I think that is the reason we have been bypassed, or we have been left behind in many areas, speaking as someone in the field. But so the chance we have to contribute is to connect these complex systems models to the problems and methods, to obtain better methods and a better understanding of the problems. And this is my general view and introduction to what I want to say. I prepared then two demonstrations or two views of these, not because they are necessarily the most exciting, because they are based on my research. So something where I will talk how this connection happens based on statistical laws, and in a second part, a more methodological approach, how methods from complex systems can also lead to better methods. But maybe I will stop first here and open for comments or questions or inputs, disagreements, or if any.
Thank you very much. I see one hand still up. Mike, is that hand still up, or is it again up?
It's still up.
Okay. So yeah, thank you very much. This is, I mean, this is a very, very interesting perspective. The whole thing about where we operate as a cultural data analytics research group, which brings together a spectrum of disciplines. Obviously, one could write a similar sort of four-liner for every one of the disciplines. And let me just add one of myself. Like my PhD is in art history and sort of 50% classical archaeology, but I found complex networks there. And so in some sense, I work with found data. So like in computer science, in my PhD, it was explanation. It was not mathematical modeling. I just identified that these frequency distributions, giant connected components and stuff like that are there. In some sense, coming from a sort of classical archaeology tradition, to study anything thing is sort of something which obviously also drives fields where, you know, sort of information is scarce, while at the same time, if you do this long enough, you end up with large amounts of data. And so in some sense, people may have different kind of experiences how they come to this. And I'm quite curious about, so you say models, so the models must come from somewhere. They must come from observation. And as you know, one of the big transformations in complexity science has been that now data, like every second abstract in papers starts with, you know, now data is available and we can measure blah, right? And so that is something which indeed, like a generation ago, there was even no funding for observational research in complex systems. Like you had to have a model, you had to model, and you couldn't go out and say, oh, I want to measure the network structure of the following large data set or something like that. So what you're offering here is, I think, a really important hand to people who come from data-driven, because indeed we need to marry these two approaches. Do I understand this correctly? That basically what you're offering is to say, okay, we come from this model-driven world, and now we need to sort of validate the models, which, inversely speaking, we need to validate our observations with the models, which is a really interesting thing.
Yeah, that's right. Yeah, I think this is, of course, an extremely simplified setting, but I think it is aimed to apply for disciplines, not for individuals, right? So I mean, I think that's yes, when I'm talking about models here, I'm thinking about mathematically or computational generative models, right? So I don't know, agent-based models will be an example here, right? So where you can design the rules and simulate them, even if they are not suitable for mathematical treatment, but also in networks, we would think about the models motivating the generation of random graphs or generation of specific observations, right? So these are mathematical computational models that yes are motivated by data, but as I will try to argue later, the data model relationships typical in complex systems are sometimes very simplified or very different from the traditional statistical model comparison or hypothesis testing. Yeah.
Yes, yeah. I have a second question. Let me raise 2 points, which I think are quite good for the audience to see where sort of our, sort of like our theoretical landscape here, sort of like in this encounter sort of is standing. So you are combining. So you do natural science and you talk about social science. And one of the interesting things is that like many people in our group, for example, come from fields that would not count themselves into social science, but sort of, this is called cultural science, cultural studies, cultural, sometimes, basically fields that deal with text, images, objects like artifacts, stuff like that, or maybe even spaces. Sort of the graphic geography and stuff like that. So one of the interesting things here is that there is an obvious question, where does stuff belong to? And I think there's one word which you had up, which is central to your talk today, which is topic models. Topic models are not models as the models you just described. They're not like equations. I mean, in some sense they are, but the topic model you get out is sort of something which is, from the point of view of a literature, language, or linguistics person, sort of an object we can talk about that has sort of like intrinsic meaning, right? So there's like every topic is some sort of frequency distribution over some words. So there is sort of the cultural artifact notion sort of like manifests itself in the model, but of course, first and foremost, in the object where you extract the model from, like some kind of textual corpus, which is not, strictly speaking, just social, but one could argue it's often the subject of some specialized discipline, such as language, linguistics, and literature, or cognition even. So there is a kind of, I don't know if you would agree, but there is a kind of hidden part of the iceberg of cultural, sociocultural products and sociocultural phenomena, which have not been tackled so far in complexity science, but need to be lifted out of the shadows. And of the social network, one of the first things that happens is people look at text. So we did this thing in the Advances in Complex Systems, the journal. We had in December, actually, a topical issue on cultural complexity, and we were not surprised that most of the submissions we got were either social or text-based, and so, or even both. So one of the key issues there is, do you think there's a moment where you would say, okay, when I say model or say models, I obviously conventionally refer to, say, equations that model some, like in an agent-based model where every agent has some set of equations and some interactions going on, or gravity, something like that. While then there is sort of this gradient where I go towards other things like a topic model, which in a strict sense still that kind of thing, but there is this kind of moment when, you know, where you can ask, oh, is that now some kind of assumption, sort of thoughts about the system, expectations, where you don't really know, is it yet mathematical, or is it still just a philosophical intuition or something like that? So how do you think there is a boundary for complexity science in that respect?
Yeah, well look, I think what I being bold here at trying to be mindful that this is recorded, but I'm trying to, what I am very critical of, and I think this applies also not only to the social science, but as you pointed out, maybe in particular to the humanities more generally, yeah. Is this naive way of this separating the qualitative analysis from the quantitative analysis. And I think here is the application of this topic modeling, as you mentioned, as it is a generative model, that it is just not viewed as such, right? So, and then treating the output of these topic models as topics, right? So, which is not, right? So, I mean, we'll come to this aspect later, yes. But I think what I'm trying to argue here is that many of this type of approach of performing quantitative and interpreting quantitative results is extremely problematic, and in fact it is true now. So this is what I am. It is through the use of generative models that we can solve some of these problems. And here, when I'm talking about models, yes, I want models that can be quantitatively connected to the data, so they require to be a generative process. And as you try to say, this is not always possible, but that allow for statistical inference. But I believe that these models are much more easily connectable to what people in the humanities will see as the generative process of the data sets, right? So something that is hidden in these methods because the assumptions are often not made explicit, right? So, or either because it's unknown or because it's simply too complicated, right? So I think that is the core of what I can contribute. I think there are much more than in what you said, but I think I'm not qualified to comment on the other aspects.
Thank you very much. Yes, go on.
Yeah, maybe we can come back to this at the end, because in view of some of the aspects I was saying, and I think here the first aspect that I'll try to go quick is around this view of what we call statistical laws. This is a concept that is core in complex systems, as I will argue, and that has been the way many people in complex systems have connected data and models, right? So what I mean by a statistical law, maybe a very famous example now from the natural science, is the Gutenberg-Richter law of earthquake magnitudes, right? So trying to reduce the mathematical notation, but unavoidably going through them, right? So this is essentially a histogram of how many earthquakes we have with a given magnitude, right? So, and we are just plotting this cumulative histogram in a logarithmic scale here, right? So there are 100,000 earthquakes, 10,000, 1,000, and so on. And the key issue here is, of course, that the magnitude is the logarithm of the released energy. So when we move in one magnitude here, the amount of the harm it does to it's increased dramatically, right? So and in fact that's an example, because the famous earthquake in Lisbon in the 18th century was a blow into the deterministic, the mechanistic hopes of reducing science to a mechanistic object. So I think it's very core to the view of complex systems in general. But the Gutenberg-Richter law is one of my examples of statistical laws. Another more recent example now that has been studied quite widely is what is called the urban scaling laws, right? So it's a different type of law where here we are seeing each dot here is a city in the USA here, and for each city we look at the GDP associated with this city. And if you make this scatter plot again in a double logarithmic plot, we see that the points fall here roughly in a straight line, but the line is not with a slope 1. So, and this is represented then by this scaling law, that the y, that GDP, scales with the population, not linearly, so not in a per capita basis, a constant per capita, but as x to the beta, right? So in this case, the larger cities have a higher GDP per capita basis. So the validity of such linear function, linear scaling, is also a statistical law. And the role these laws played in complex systems through more than a century is that once you observe sufficient evidence of that, right? So, and people have claimed that these laws are now valid, right? So they were often made equal to empirical observational laws, to even Kepler's law in a tradition of social physics, a very unfortunate term, but that will be the view from the field. And in complex systems, we will see this as an emergent feature to be explained. And once we are convinced of its validity, it comes the models, right? So we would then think about a microscopic world. Maybe in the case of avalanches or earthquakes, could be typically springs and blocks models mimicking tectonic plates, maybe, that will give rise to this macroscopic observation, right? So, and then we would say that these microscopic models explain these observations. So these mechanistic models explain the observations. But then we would also use these laws for risk estimations and for applications. So for instance, if you think about the first statistical laws, right? So about inequality, maybe associated to the work of Pareto at the end of the 19th century, if we translate it to our modern data science world, we could think that the number of citations of papers is some measure of success or of attention received by these in an attention economy setting. We would then think that the same Pareto law of income is also somehow valid for the attention received by different papers. Now, again, our histogram, cumulative histogram in double logarithmic. So this power law distribution of income applies to papers published in this journal, but also for incomes of firms in France, and I believe in Japan as well. So if this is the statistical law, we observe the explanations. So many of these different models in different areas go back essentially to the work of Yule or Simon in the mid-20th century, which point to a rich get richer phenomenon, right? So the more you have, the more you get. So and this appears in different flavors, such as Gibrat's law or proportional growth, and these are used to explain this. But again, it's the same dichotomy: is that the law, and the empirical statistical law, and then a mechanistic explanation. And we can try to tabulate that. It goes back also after Pareto, also the works by Auerbach and then Zipf, what is known now as Zipf's law of cities, originally proposed by Auerbach, a physicist, and now explained by Gabet and others through similar preferential attachment or rich get richer models. The works on earthquakes there that I mentioned motivated the works of self-organized criticality networks, right? So what some now call network science. One of the founding papers by Barabaji and Albert on is essentially the explanation of such a fat tail power law degree distribution through a preferential attachment model, which is essentially a Yule-Simon model for networks. And these are all power law distributions. There are, of course, other allometric scalings, as I mentioned, urban scaling, that goes back to much further. And also there are statistical laws that are based on the dynamics on inter-events and not only power law distributions. And so this has been a very successful story and very recurrent story in complex systems, until maybe a few years ago when people started criticizing it, right? So I think maybe that is the first very prominent paper in science about the critical truth about power laws. More recently, some started to dare to claim that scale-free networks are not typical, they are rare. And after that, there are even the tabloids or the popular science venues started telling the opinions of leading scientists about that, right? So, and some people reporting even in some of the most prominent conferences in network science, it is controversial now to say if fat tail or scale-free networks are typical or not, right? So a blow at the core, at the foundations of complex networks or network science. So what happened? So why we went from statistical, from scale-free networks everywhere to nowhere in 10 years, in 20 years? Even if you don't care about this question of whether it's a power law or not, if we are not trusting this statistical law, what does it mean for the models and for the applications? So that we discussed before. So that is the question, how we went from power laws everywhere to power laws nowhere in 10 years in complex systems. And I see some people laughing. I think you maybe read some of this paper, recognize these debates that are often very heated. And so the question is why? And a very valuable suspicion is that we have more data now, right? So we are in the data-rich world. Maybe we have more data. Let's take Zipf's law, the Zipf's law now for word frequencies. So if this is a figure from Zipf's work from the early 20th century, where he got 3 novels, and he counted the frequency of each word and then plotted in these rank frequencies. So this is the most frequent word in book A, appeared here maybe 8,000 times. That's this, sorry, that is this point here. It's not working now. Mouse pointer is banned. Yes, no. Okay, so this point here is for book A. The most frequent word appear 8,000 times, the second most frequent word, and the third one, and so on, for book C and B, and they fall roughly in a straight line. And Zipf proposed that it should, his law, Zipf's law for word frequency, decays as 1 over R, 1 over the rank. So it is equivalent to the histogram version mentioned before. But so this is again a double logarithmic plot. So what we did few years ago with my PhD student Martin Gerlach, we look at Zipf's law using the Google Ngram corpus. Right? So Google scan allegedly around 5% of all books ever published in English and provide to us the frequency of the words. And these are the rank frequency, the Zipf's plot for the books published in 1800, only the books published in 1800. And here now, the ones published in 1900. When we see, if you go, these are completely different books, separated by 100 years. But if you see, the database increased. There are more books in Google's Ngram database. And that's why we go further here in the plot, here down. We have more data here in the tail. But otherwise, so this tail increase, otherwise, this functional distribution looks very similar. And if you go to year 2000, or even if you combine all of the data, we see the same pattern, right? So I think in the same spirit of Zipf, right? So of course the functional form here changes, and in fact there is a decay that is faster than Zipf's proposal, but otherwise, and we compared here different functional forms and came up with this proposal of a generalized Zipf's law. So that is a Zipf term in the beginning, and then after a given threshold here B, we have another power law with an exponent gamma larger than 1. And from our statistical test, this was the preferred functional form. But in general, in spirit, the concept of Zipf's law is valid. In fact, we tested in different languages as well, and these functional forms seems to be the best or the second best in all languages with the different parameters B and gamma. But I would not consider this a falsification of Zipf's law. It is maybe an expansion, a generalization. But the concept of statistical law, I would say, if anything, is corroborated. It is reinforced. Not that a simple functional form can describe such a variety of data sets. And so I would not say that this is the reason why people started refuting all these power laws. And in fact, the answer is that there are better methods. And in the field of complex systems, they are often attributed to the publication of this paper that in a great extent brings to the area statistical methods that were known before with some important modifications, and it received a lot of attention, more than 10,000 citations by now, and that is what led to this change in conclusions. And what was Clauset, Chalice, and Newman proposing? They were correctly indicating that if we have a histogram that in this double logarithmic scales, they falls roughly as a straight line, we should not simply fit through some least square methods a curve that looks good against this method, right? So this is not a good statistical practice. In particular, this logarithmic transformation is a nonlinear transformation. When we fit a straight line here, we are assuming that there are uncertainties in each of the points that are of the same magnitude. And of course, there are the uncertainty for in this area of the plot should be much higher because we have less data than when we have here, right? So instead, what good statistical practice tells us is that we should use a maximum likelihood approach, in a statistical frequency setting. Maximum likelihood principle will be telling us that we need to find the exponent alpha in this case that maximizes the likelihood, or equivalently maximize the log likelihood. So, and if you take the observation as being independent, we can decompose the log likelihood as the sum of the log of the probability of observing a given point of magnitude x, a given observation of magnitude x, where x now is, this probability is now given by this power law, and this can then be computed analytically. Right, so, and we can then generate, once we fit this maximum likelihood estimation, we can generate data with this distribution, and we will then compare, make a statistical analysis comparing what this data generated from this process, which I called here a surrogate, with my observation. In particular, I can define a distance, typically a Kolmogorov-Smirnov distance, but a particular measure of distance of how well my points agree with my fit. And I will compare how much my distance in the data compares with the distance in my surrogates, in the artificially generated data. And the value of the distance that goes beyond what I observe in my distance is a p-value, is a probability of observing deviation equal or larger than the one I observed once the data is generated from my new model, right? So we can then, typical thing would be do a hypothesis testing and reject this depending on the value of the p-value and the threshold, but we can do also other statistical analysis of confidence intervals. Right, so the core point here is correct, that we need to go beyond very simplistic least square fitting. But this methodology and the application of this methodology essentially led to many of these criticisms, right? And while the basic ideas here are correct in the view of the need to go to a maximum likelihood estimation, there are very important differences, and now I will criticize this approach. So it's, first of all, I think this maximum likelihood fitting is very different from the scaling arguments in statistical physics. But on a technical ground, there are two hypotheses behind these methods, right? So the first hypothesis is that, yes, the data is generated from this distribution, and in fact, with a given parameter alpha, right? So what we are testing in this hypothesis testing is the maximum likelihood alpha only, not the distribution as a whole. But there is a second hypothesis that is very important, is that the observations are independent from each other, right? And we all know that the observations are never independent, right? So no data set of interest, in particular in a complex system setting, has independent observations, right? So, and in particular in networks, that it's even not clear what does it mean to be independent, because the degree of the nodes are all interconnected, right? So when we reject a hypothesis, if we do hypothesis testing based on this hypothesis, we are rejecting both hypotheses. But we already knew that hypothesis 2 is not valid. So formally, this rejection is meaningless, right? So because we are rejecting something that we already knew it was wrong, not valid, right? So how can we interpret the rejection as being based on the first hypothesis and not the second, right? So for instance, this here is the autocorrelation function between earthquakes separated by tall days. And we see that in blue here, the autocorrelation function, it takes almost 800 days until it is close to zero, right? So zero here, this is what we would have expected in orange for the independent data. Right, so if you are rejecting Gutenberg-Richter law based on this assumption, it is meaningless, because we are assuming that they are independent when they are not. Okay, so of course we could say, can just a violation of independence lead to rejection? And so we generated that. So we generated a Markov 1 process, a stochastic process that we know satisfy asymptotically a power law, but that has correlations, right? So in orange is the IID, the identically independently distributed data, while in blue is this Markov process, which are given correlation. And if we perform hypothesis testing, here we are performing estimations of the error or our exponent alpha, right? So the uncertainty of our estimated exponent as a function of the number of points. So the size of my data set. Of course, when I have more and more data, the estimation converges to the true value, but the fluctuations are large. But if we do hypothesis testing, we end up rejecting. So this is the rejection rate as a function of n. And we see that the rejection rate goes to 1, meaning that we reject always for any observation for sufficiently large data sets. So we are rejecting based on, even though the data is truly power law. Okay? That's a problem, right? So what have I done with co-workers? So there are two things we have done. First, we proposed better statistical approaches, and then second, we propose in a particular setting how to fit the generative models. I think the first aspect here is more technical. I will go very quickly through that, right? So one approach is just to recognize that because our data sets are correlated, the number of independent points that I have is reduced. So the recipe we propose here is to estimate this correlation. If we have a time series, this is relatively straightforward. And then simply consider that the effective sample size that we have is not n, but is n divided by this correlation, because that's the number of effective independent points that we have. So we will then perform hypothesis testing, but not with the size n, much larger size, but with this reduced size. And with a smaller data set, it's harder to reject. And like in the artificial correlated data here, we don't reject. So which is the correct answer? We don't reject. And we tested this in different data sets. For instance, for earthquakes, we also end up not rejecting. In other areas, we end up rejecting, or it is unclear. Another more sophisticated approach we proposed more recently is to build better surrogates. And we build on this idea of constrained surrogates, where we can incorporate correlations in the data explicitly, but also we can obtain better statistical tests. In particular, we impose as a constraint the likelihood itself. So all our surrogates have the same, so that is what we propose in this recent paper here with Jack Moore. All these surrogates have the same likelihood under the power law hypothesis. And this allows us to test all our alphas, all the exponents simultaneously. So to do an actual hypothesis testing of the full distribution, power law distribution, and not only of a given alpha, not only of the maximum likelihood alpha. And in fact, we also introduced additional correlations in this data. And here is just an example. The rate of rejection for the earthquake data set that we had as a function of sample length was also going to 1 as before, but when we use our constraint method, constraining on ordinal patterns, imposing some correlations, the rate of rejection stays where it should be, or stays at the 5% threshold, so in the non-rejection regime, at the 10% threshold here, the non-rejection regime. And this works with different test statistics, but that's quite technical. Yeah, I will rather focus on the second aspect, which is, so this is one proposal. We can obtain better statistical methods to analyze, but I think what is more relevant to the main point of my talk here is how we can use generative models and fit generative models of the data instead of using statistical tests or methods that do not talk about how the data was generated, right? So, and I'll focus here on my work on urban scaling laws that I motivated before, because a very similar story happened here, right? So when people were analyzing, still are analyzing urban scaling laws, the typical approach is, again, to remember these were cities and observables in these cities, right? So each dot is the GDP here of a city, but people look not only at GDP or many other observables. So the temptation here was to fit a straight line here, to use a least square fitting for this data set, right? So people will fit a straight line, compute this R square, this correlation coefficient, and the high R square is often taken as evidence of a good performance, and then compare the confidence interval of this fit with a given beta. And if this confidence interval is away from beta equals 1, the claim was that this is a nonlinear scaling. There are similar problems as highlighted before, that the least square is a maximum likelihood estimation only in some cases. R square is definitely not a measure of statistical significance, and the confidence intervals can only be taken if the data is sampled from our true model, which is often not the case, right? But very intuitively here, we can also see the problems. We cannot deal, for instance, with observables where the observable Y is 0, right? So if you have a different observable and there is none of them in that city had no GDP, we cannot take the logarithmic transformation, right? So it's clearly a possibility, but this fitting will ignore. Or also in this example, related to the correlation criticism I made before. So I'm highlighting here 2 cities in the USA. San Jose is in California, close to the Bay Area, close to other big cities. So we see a high GDP here, right? So in this approach, it was taken as an independent of observation, while we can suspect that the fact that it has a high GDP is based on its location, of its proximity to other cities. And the same apply here to Trenton in the east coast of the USA. Yeah. I see a hand raised.
Yes, a very quick question in between. So in this plot, you make this point that, you know, we have places where we don't know what's going on, but we have also vast amounts of data where there is more going on than we see in these plots. So the plot on the x-axis starts at 10 to the power of between 10 to the power 4 and 5. So places that have, say, 50,000 inhabitants. And on the y-axis, we also start with, you know, in the 10,000s or whatever, or the thousands, sorry. So if we complete these places, and there's many, you know, Peter Dodds has this allotaxonographs. I've done this for birth and death in cities. So if you go all the way down, you typically get a sort of fanning out that sort of with, you know, sort of square from the diagonal. And this very neatly sort of goes all the way out to 1, as you say. But then there is these places that we know, like, for example, you know, there's places where there is no births, but only deaths, like plane crash sites or something like that, and vice versa. Places where you have only births, like birth stations, very few people die there unless are documented. So there's this kind of thing where you could actually complete this graphs, but while what we're doing here, and you've done this, and you've mentioned a bunch of these examples, we're always looking at particular areas where, you know, there is something like a straightish line going on. And so there is a kind of a question is like, do you have this feeling sometimes when you say, I want to actually go down? Like this has been done for conflict data, right? There's the Richardson paper, where there's a clear power law, and then people look at terrorist attacks, and then you can look at murder and stuff like that. So you get a really nice sort of scaling. But in most of the literature, if I'm not mistaken, of everything that you cite so far, we're basically looking at the you know, lower end or upper end of the tail, depending on like how you define what's in the tail.
I know part of this literature. In fact, there has been a lot of debates about how do you define a urban unit here, right? So what is do you use a metropolitan area? What are the boundaries? That is very, very detailed work, taking commuting time into account. But in fact, I think that some of the more recent works have indicated that the validity or the exponents of these laws depend on these definitions, depend on the threshold. What is the minimal city we have? There is this work by Elzar Kautsky and co-workers indicating that the number of cases in which these scaling laws that are non-trivial is reduced dramatically if you include better definitions of metropolitan areas, right? So I think that there is in fact a symptom of this mismatch between the data analysis methods, right? So and the process is taking place. But I think what the criticism I'm making here, or the contribution I'm trying to make here, is to try to propose a model of how this data is generated that has the potential to take these things into account, in particular to take spatial location and spatial interactions into account, instead of simply debating whether there is a boundary here and then this is independent of what is next, right? So it's a thresholding, and how do we threshold? Right? Yeah, but absolutely, yeah, the threshold we put here have a big impact, no? In particular because of Zipf's law, right? So that the majority of data points falls here, right? But they are very small towns. But if we are doing a least square fitting, we are giving the same weight to this town here than to New York City here, right? So we are just want the line to be close to them, right? So this is already showing how absurd it is, right? So because this problem, right? So I mean, or how delicate it is, or how tricky the methods you use are, if you wish, right? So we propose some maximum likelihood models with my students in 2016, and more recently I incorporated these spatial interactions here. But yeah, I will quickly go through the ideas of these papers, right? So that I think address some of the points you made, Maximilian. Yeah. So the idea is now, in a complex system spirit, to try to think about how are these observations generated, right? So, and then use these to analyze the data instead of fitting straight lines. Well, I think in all the explanations that often also follow, right? So this literature often follows the same pattern. First, there is a fit, and then there are mechanistic models. So if you look at these mechanistic models, they often have this idea. Now, I will motivate here by a token of GDP, but it applies to other areas, is that a token of GDP can be attributed to a person that lives in a small town or in a larger town. But there is a higher probability to be attributed to a larger town because she has better interactions, better chance to interact with other people. So there are more interactions that are possible for her than for him. And that's why the chance of attributing this token of GDP is higher. Right? So in other examples, the interpretation could be different, but that is at the core of the idea. So you write, what is the probability that a token of observation is attributed to a person J? And I would say that this is proportional to A, where A is a pairwise interactions, okay? A to some power beta minus 1. This will be the same beta, but bear with me. Z here is just a normalization, okay? So it's just because the probability needs to be normalized. So between 0 and 1, that's just a normalization. And I will write this pairwise interaction A, this value that is coming here, as a sum between interactions between pairs. Okay, so, and here is where we can incorporate some distance, we would say, and distance here could be a commuting distance, it could be a social distance. Eventually, I will use, just for simplicity, a geographical distance between locations, but the framework could be expanded, right? So, but that is how my data will be generated. Each token will be attributed by chance with a given probability given by that. And how do we model these distances? Well, if we take what I call here a city model, if I just say, well, the interaction is 1 if you are in the same city, or 0 if you are in a different city, then we recover the previous case. We recover a model where we only consider inside city or an outside city. But in fact, what we recover here, and that was in our first paper here, well, these notes are not helping now, but what we recover here is a model that gives the same weight to each individual, okay, to each individual, not to each city, because we are drawing tokens, right? So, and that's, again, it's a model where New York City will have a weight 10 million, well, because we are attributing these to individuals and not to cities, but otherwise we will recover here the same approach of either you are in the city or outside the city. Other models, such as gravitational model, will consider that the interaction between individuals will decay with some scale alpha. Alpha here is always a measure of distance, of how the interaction decays with distance. We could also propose an exponential model. We can, in principle, propose any model, because we will let the data analysis choose the model. We will do a proper model comparison. But they are extremely simple models, at least here, to allow for some analytical treatment, right? Because if we write the probability like that, we can then just compute the probability of allocation of a token to a city I by summing the probability of individuals here, of a person. We are summing them over all individuals in a given city. So I'm writing here the probability of a city C receiving 1 token. And then we can write this, we can bring up here the interaction between the users, between the individuals here. And we can write down the probability of having a given observations as just a multinomial. Overall, here the product goes overall the population. Okay, so we can then take the log of this probability, and this is then a log likelihood, as considered before. We can write this explicitly here, and we can then move even to a Bayesian framework here and do some proper Bayesian model comparison, right? So we can assign priors here. I'll be using, right? So I will write here. So what I wrote before was the log likelihood, so the probability of observing a given data, given my model, and the M, so the model class would be either the per capita, the CT, gravitational, or exponential model. Per capita here means just that the scaling law has a beta equals 1, right? So, and theta here are the parameters of each model class, right? So, and so these are then the family of models that are the different models that I will compare based on Bayesian model comparison. And for instance, here is the case where my observation Y is the extent of roads in cities in the USA, and this is typically mentioned to be a sublinear scaling. So larger cities require less roads per capita. And in fact, if you fit for alpha 0 or alpha 1 here, we will get the result where we don't take spatial cases into account, right? So that's our CT model. This is the value of beta I obtained there. And now if I vary my alpha, I vary the length of interaction that I have, well, the gravitation and exponential model are taking this into account. What I am showing here is that the optimal value of beta, right? So the optimal scaling parameter depends on the length of interaction, right? So that the spatial distance here changes the value of the scaling, right? So, and in fact, the alpha here, the dependence here goes all the way to around between 10 and 100 kilometers, which seems to be meaningful for the interactions of users. And but maybe more important here, I am comparing here the posteriors here of the models. Now, so and in this representation here, the larger values are preferred. So we see that the larger value that we observe here, this is a model comparison, are for the gravitation and exponential model for values of alpha around this range that I mentioned, right? So, and in this range, they are better than the CT model, right? So that is what we observe here. So the fact that the blue and the red curve here are above the dotted line is indicating that from this model comparison point of view, they are better than the model that doesn't take location into account. And they are better in a range of interactions around 50, which is meaningful, which is interesting, right? So we have simple models, we have more complicated models. For this example, the more complicated models are preferred. It is not always like that. So I apply these to 5 different cases. And here we are using this description length measurement. Here is how much I can compress my model and data. I will not enter into the technicality, but here the smaller these values, the better. So we see that different data sets show different best results, best models. For the GDP, it turns out that the one without location provides a better description, but in all other cases, the inclusion of location is meaningful, right? So that is an example of a generative model that can be used to infer parameters of the statistical law and test whether these statistical laws show a non-trivial scaling or not. Yeah. And let me conclude then this first part. And what I try to convey to you, this idea of statistical law is central for complex systems. It is one of the main mechanisms that complex systems research has used to connect models and data. And I think the more data sets we observe, these statistical laws remain relevant. Right? So maybe remain even more relevant because we have more data, we have new data sets, and they seem to continue to appear. But we have to be careful about how we validate them, how we test them. We have to be careful in particular about also using simple statistical tests, in particular based on independent assumptions, right? So, and in general, the validity and the usefulness of these statistical laws should be evaluated based on mechanistic models, on models that generate data set of the same type that you observe. And if we can compare these models, and then we can obtain a more interpretable and robust evaluation of these laws. And in particular, we can attempt to take into account correlations and other patterns that we know exist in the data, and not only account for them in our models, but also account for them in our data analysis. The decision about which model is best accounts for these generative processes and these correlations, and it's not separated as traditionally done in complex systems as the data analysis and the mechanistic models as two different steps of the analysis. Now, but they should be coming together in a statistical inference way. So let me finish then this first part on thanking all my co-authors, and then I'll take questions now. Yeah.
Thank you very much. I think this is fantastic as a summary, and also begs a lot of questions. So in this audience, there is both tailologists and people who don't deal with tail distributions. And so I think this is a really interesting thing for those who are not dealing with that. Every one of us who started 20 years ago getting into this sort of power law world, or not so quite power law world, went through this kind of school. And even if you don't understand something right now, I think it's very therapeutic. And at some point you will see in your own data that this kind of stuff appears. Even those who at the beginning said you're not doing complexity science, I know for a fact, just by the topics that you're working on, that complexity in your topic is very much inherent. So this is sort of in general also a little pitch for those in the maybe aftermath audience on the internet. Now, if we go back to this, for those who actually are familiar with that, maybe there is some concrete questions. I see Mike has his hand up. I have also a sort of reconciliatory question regarding these two worlds, even though I'm very much like Eduardo, not a friend of this split of the humanities versus quantitative. So Mike, go ahead, please ask your question.
Thank you very much. It was very interesting and super relevant, at least for me. And I've picked up some ideas from there. And actually, I have a couple of rather technical questions about what you have just talked about. One concerns the frequency distribution in language, this 2-Zipf thing. As far as I vaguely remember from your paper, you have seen that this second power law for real world words, it changes in time somehow. This parameter gamma is non-stationary. So basically, I wanted to ask, number one, do you have any speculation about why, and whether it is intrinsic to language or because we have changing amount of data for different times, and whether it is different and how much it is different language to language. That was one question. Another question basically is related to me trying to apply your urban science thing to something we are doing here with historical news data. basically, am I right to understand that you basically can do
should I maybe
yes.
try? Should I maybe take the
yeah.
Zipf law question first? And yeah, thank you, Mike. Yeah, these double power law, a very similar double power law analysis had been proposed before, and there were interpretations of these regimes in a distinction between a core vocabulary and a non-core vocabulary. So the values up to B star will be a core vocabulary, and after that will be a non-core. What we did look at is about the flow of words from core to non-core, and it's a very substantial flow. And I think the change of words in this rank frequency distribution is very substantial and can be quantified, and is in fact changing even faster over time. This is an analysis we did. The functional form of these distributions, I think, was quite robust over time. We were not seeing a dramatic change in the values that we estimate over time, but more in terms of how fast the words are changing within this rank. Does that make sense? So what we are plotting here is the rank, but which word occupies each rank changes over time, of course, right? So new words are invented and falling into use, and that change we quantified to be accelerating. But the functional form itself of the Zipf's law, I think, was not changing dramatically, if I recall correctly. But yeah.
So that is. Can I ask a follow-up question on this? So we did this work on rank stability, which sort of there is. You can think about it in two ways. There's a score stability, and there's a rank stability. So one gives you the relative market share of the word, say in a year or in a decade, and the other one gives you the actual rank. And so, for obvious reasons, you can be score stable, like appear in 20,000 books, but still fluctuate in rank. So score stability should be more stable than rank stability. And it turned out that in many different systems, being stable only happens basically towards the top and is really, really, really rare. But then we walked into this project in 2010 or something with the assumption that there is a canon, like a core, and a less stable sort of tail. And then that didn't turn out to be true at all. But you can be very rare indeed and still stable. Like, for example, imagine a church where sort of 10 visitors go there every 5 years, and they do so very regularly because there is some kind of funeral, anniversary, whatever. They still do that. So they do that very regularly. So it will be sort of part of the stable part. So this change between these two regimes of like a core and the periphery, I think is sort of something which should be emphasized a lot, because it also means there is no such thing as, a stable set of professors with a stable set of topics that sort of own a field, because the core of the field itself is changing. And I think that is something which is still buried in these distributions, and more so in the dynamics of the distribution, which obviously is, there's some kind of competition with your Bayesian models going on, right? Because you have all these different instances you compute, and then you sort of try to figure out how realistic your stable distribution is. But then if the distribution changes over time all the time, then it's really hard to separate these two things too. So do you see a progress in this in the shift from, say, static frequency distribution to a more dynamic kind of perspective?
Yeah, look, the point is that there are here 10 to the 7 words, right? So yes, each of them is doing their own dynamics, right? So it's of course a very rich area of analysis, and there are many different things that can be done, right? So and I just the the fascination for the statistical laws is that they seem to be something that is stable, right? So that they seem to be an universal feature that if we take 1800 or if we take 1900, right? So these remains the same, right? But so what we did comparing this evolution, I mean, from my experience, it depends very much on the measures you use to quantify these dynamics, right? So, and again, here, depending on the measures you use, you are either dominated by the most frequent words that I have control most of the tokens, or you are dominated by the least frequent words, the hapaglegonema, that control most of the types, right? So that is also why I think when analyzing these dynamics, depending on the measure you use for quantifying rank stability or dynamics, you will get different pictures, right? So that is one of my experiences in these. And yeah, but otherwise, in fact, another, I think, point that has not been fully explained, or I think the explanations for the appearance of Zipf's law in word frequencies often will not describe correctly these dynamics, right? So if you are thinking about a model that, if that is your question, or reformulating your questions in these terms, do we have models that can explain the emergence of Zipf's law and at the same time explain some of these dynamics? I don't think we have.
Mike has a second question, I think.
Yeah, well, first of all, have a little follow-up on this first question. So we just seen from the picture you showed that, for example, German and Russian have reasonably different power law tails. Is there any reason to, any understanding of why it is something like this also?
Yeah, we did look at the B star at this threshold, and this seems to be related to inflections and declinations in Slavic and in German as a mixed case. So it has to do with the tokenization and the inflection. The power law exponent, we don't know. We haven't been able to say.
Okay, yes, thank you very much. And there's basically the second question is concerning this urban scaling part of what you were talking about. Am I right to understand that basically you can, if for example you have, say, I don't know, additional binary variables describing your cities, like for example, belonging to one state or another state. And if we are thinking United States, it is more or less with the same methodology, you can introduce this sort of variable with your generative model and evaluate it.
Yes, I haven't done that, but I think one could expand this model to have, of course, there are different features of the cities that could be taken into account to go beyond this one-dimensional analysis. I think that is definitely the case. Yeah. I think one could expand it. What in these analyses, and there is a GitHub repository with these data sets, what we are looking there in the second paper is the location, is the latitude, longitude, and so from there we compute these distances. But yes, so we could have a categorical classification in terms of states and use that as additional variables. Yes, it's a good point. Yeah.
I have a question which sort of like, I hope, connects the humanities perspective with the natural science perspective, which is like, if you are a complexity scientist in the natural sciences, if you're not a biologist, not a cognitive scientist, but just a physicist, and you apply to the, say, European Research Council, you will submit your networks thing either to nonlinear physics or to condensed matter physics, and it will push you back and forth because there is no networks panel, there is no complexity panel. Now, if you're in the humanities suggesting that you quantify complex networks or you quantify complex patterns in statistical laws, out of 5 reviewers, at minimum 1 will tell you you're undecided between nomothetic and ideographic, between law discipline and event discipline. Event disciplines like history, where everything is special all the time, versus law disciplines where everything is the same, or all the air molecules do the same thing, which is obviously also preposterous. So the key thing is, if I walk into humanities department and say I want to measure the statistical laws of language use, maybe not in computational linguistics, maybe not in certain areas, but certainly if I talk to, say, an English literature scholar who is qualitative, most art historians would say, that's like not how art history should be done. If I want to measure statistical laws of, say, the frequency of attributes in paintings, for example. So we talked about this about 10, 15 years ago when I first joined Barabasi Lab, that we cannot use these kind of concepts. And one compromise we end up with is fundamental patterns. And in this discussion, one thing that came to be was the awareness that, if you hunt for statistical laws and you find one, you assume it to be a law. While if you say, okay, there's people who put this in question, then the question is, how law-like is the whole thing? And then the key question is, what's the ecology of law-likeness, so to speak? So the question is, do we beyond the kind of stuff that, there have been turf wars? I was the one who snickered before, turf wars between power law, not power law, stretched exponentials versus power law, whatever. So there have been multiple iterations of these kind of things. But how about just looking at these things and looking at the broader distribution of distribution, so to speak? Is that something which you think is that is feasible, or will we be tied to certain laws that we can test or not?
Yeah, I think the reason people focus on power laws are there are different reasons, right? So, but the analytical simplicity, the connections to maybe even extreme events statistics, right? So to generalize central limit theorems, right? So in that onset there. So I think this is and scaling arguments, right? So that are the critical phenomena in physics, right? So there are all these theoretical, all these reasons for the focus on this particular. If we start now looking only on families of distribution and maybe model comparison between them, I think this is a alternative approach. But I'm not sure we will ever capture all these other motivations behind power laws. So that is one comment. But I think more generally, my main point here is that what is most relevant is the generative process behind this power law. So, I mean, this is what is giving us insight about it, right? So in case of networks, it's not about whether the distribution is scale free or not, the degree distribution, but whether the preferential attachment process in one way or another is responsible for the onset of that. And of course, this is a much more difficult thing to evaluate. It's not a matter of just fitting a straight line or not, but it is also, I think that is the point. But what I think is very problematic is the refusal to understand that these proposals are statistic in nature, right? So these laws that we are evaluating here, they are probabilistic, right? So I can write a text that violates Zipf's law, right? So we can go there and create. I mean, there are all these whole fields of poetry where you can constrain your vocabulary or constrain your generative process, right? So if we are thinking about these regularities, both in the data sets of observations that are noisy, but also in the space of realizations, in the space of possible distributions, we need to reason it in a probabilistic, in a statistical sense. And I think this is the point that people in complex systems have missed and have ignored and have treated them as some sort of new Kepler's law, where we can now perform analytical calculations, assuming their validity as some sort of empirical law, right? So as if we have access to the question whether things are valid or not, independent of the theory. And I think this is a lesson physicists had learned centuries ago, that you cannot test things only, the validity of statements only based on experiments. That is always the analysis of the experimental data always involves theory, right? So we are always testing observation and experiment theory together, and the same is valid for these things, right? So when we are testing these, we are testing the generative models behind them, and so we need to evaluate them, their validity, together with the models that generate them. Yeah, that's, I think, the point, the main point I'm trying to make. Yeah.
Yes, thank you very much. Very, very beautiful conclusion also. We got about 35 minutes to go, and you have a second block, which I think we're all curious about, because it's about topic models. So please go ahead.
Yes. So the second aspect in this question, how complex system can contribute and in fact learn from this new data-rich world we live, what I want to emphasize is the the creation of better methods, right? So we tend to often think that it's impossible to beat machine learning methods, and often it is the case. But I think this idea of looking at formulating methods as an inference on a generative process can lead to better results, and this is what we looked at the case of topic modeling. Now, so the general setting, we have a collection of documents here written in a given language. So, and in addition, we have also additional data about these documents. It could be some metadata, so tags, or we could be also links between these documents. Now we could think that in a Wikipedia setting, each page is a document. There are hyperlinks between these documents, and there are tags that are classifying this document. And so this is our data set. And in general, our interest is to cluster these documents, to quantify the relationship between them, maybe to summarize, find topics, find missing links between documents. And of course, we will be using some mathematical and computational methods. So one way of looking at topic modeling, right? So topic models are used to be the dominant methods in this area, are still very popular and widely applied in many applications in the humanities. So we will use this bag of words approximation. We will look only at the counts of each word type in each document. This is a very large and sparse matrix, right? So if we keep going to rarer and rarer words and more documents, most words appear 0 times in each document. So we can view the problem here as a dimensionality reduction of trying to write these large sparse matrix as the product of 2 denser matrices. So, and we use an auxiliary variable here, which we call topics. So we will have the distribution of word types in topics, and then the distribution of topics in documents, and the product of these matrices will generate an approximation, or will be modeling our original data, right? So these ideas go back many decades, right? So a very important step forward in topic modeling was the probabilistic latent semantic index, which essentially provides the likelihood of such tests, right? So the words are sampled randomly, given a document and a topic. So, but maybe the breakthrough or the popularization here came with LDA, the latent Dirichlet allocation, which essentially regularizes PLSI by proposing a word topic and topic document distributions to follow Dirichlet distributions, right? So, and the choice for Dirichlet distributions is based on being some computational convenience, let's put it that way, that it's essentially not needed nowadays with modern computational methods. But this allowed us to perform topic modeling in a more controlled and successful way. So the network approach, so the contribution I'm talking here is to identify equivalence between this problem, a mathematical equivalence, so to build on a mathematical equivalence between this problem and a problem that arises in networks, a problem of community detection in networks. Right? So the translation here is that we will see this word document matrix as a bipartite multigraph. Right? So we have now two different types of words, of nodes, so word types and documents, and there are multiple links between them corresponding to the word tokens, to how often that word appears in each document. At this stage, it's an equivalence. So we will then write this adjacency matrix. The terms in the diagonal will be 0 here because the topic classification here, what we will attempt to do here now is in the framework of stochastic block models, we will try to classify, to group the words and documents into blocks. And in a stochastic block model perspective, this is a family of random graphs that will generate the edges, the links between words and documents, only depending on the block assignment of documents and words. And as was noticed by Ball, Carragher, and Newman in 2011, there is an exact equivalence between PLSI and a specific, particular stochastic block model. But what we then came up with the idea is that, well, there has been a lot of progress in community detection methods based on SPM. So essentially, they are essentially better Bayesian approaches, not better choices of priors, hierarchical priors, on specific SPM. So in that sense, we can now think our SPMs in view of the equivalence we have, right? So we can use this equivalence to now consider our SPMs as, when applied to these specific bipartite networks, as topic models, as different Bayesian approaches to the problem of topic model in PLSI. Okay, so what I will be showing here in a didactic way is just a comparison between LDA for topic modeling, and we did very few modifications in these existing methodologies of SPMs that are increasingly widely applied for community detection, for the problem of identifying communities in networks. Okay, so, and the first comparison we did was using synthetic data. Okay, so it's a very simple setting. We created documents based on 3 topics, and we are plotting them in the simplex here. So, right, so there are topic, if you wish, each vertex here of this triangle is one of the different topics, A, B, and C. These are the topics. And what I am plotting here, the bright colors, is a distribution of the distribution of topics, right? So in this first example, the documents are either in topic A, B, or C. In the second example, the documents are a mixture of the 3 topics, A, B, C. And in the other 2, they are a particular choice, right? So there is no reason to expect a priori that documents will be in one of these cases, right? So, but it turns out that the 2 first cases are Dirichlet mixtures, right? So the priors assumed by LDA, while the 2 others are non-Dirichlet mixtures, right? So, and in fact, when we look at, so we now generated documents, hundreds of documents like that, and then we infer from these documents the topic distribution using LDA and using our stochastic block models approach. And in the 2 first cases, both are roughly agreeing. They capture the right mixtures. But when we go to the non-Dirichlet case, LDA fails, right? So while SPM is able to capture that, right? So this is showing that the prior choice, the Dirichlet priors that LDA assumes for matter, right? So, and that it struggles to find things that are outside of their priors. Well, the SPM formulation is more general, is the prior assumptions are less restrictive, and so it's able to infer this structure. Right? Well, this was a very simple example, but it's a simple toy model that is showing the limitations of Dirichlet-based topic modeling. Right? So we did other analysis, again here based on this description length principle. So this is essentially a quantity that we will be using for doing model comparison, that is essentially taking into account the description of the data given the model plus the description of the model quantified in bits here. So the least the better, the more I can compress information. We generated now synthetic data from a Dirichlet mixture. 10 topics, 10 million documents, and we put some Zipf word frequency just to make it more realistic. And what we obtain here is, here we are showing the comparison between the description lengths from the LDA to our SPM approach, right? So for small length documents, the LDA obtains a better result, but relatively small documents, in fact, around 15 words or from 10 to 20, our SPM model provides a better compression of the data, even though the generative process is within the LDA generative process. Right? So this happens because LDA is spending a lot of parameters, if you wish, or a lot of model description in things that you can compress much better with much less assumptions. Right? So here we are showing that SPM can beat LDA even in the large data size in the regime where the LDA favoring LDA in the generative process. We applied also this to different large data sets, compare the description length for LDA for increasing number of topics, awful large numbers here, but the main take home is that the description length we obtain for SPMs here is smaller. That this value here in this column is smaller than for any number of topics, right? So, and in fact, the advantage also, one of the advantage of this approach we are using from my co-author Tiago Peixoto is that it infers automatically the number of blocks of documents and words, right? So while at least in the original LDA approaches, the number of topics is something that requires additional analysis. And so here is an example of what we obtained from applying SPM to very small data set of 63 Wikipedia articles. On the left, we have the documents. So we are showing the title of these documents, showing how they are clustered. And in fact, that's another advantage of this method. It automatically clusters the documents into groups, right? So you don't need to do an additional clustering of the documents based on their topics. So, and on the right we have the groups of words. So we observe that the non-overlapping blocks communities provides a better description. So in this case, the topics are reinterpreted as simply as group of words. They are shown on the right. And we see some results that are expected, right? So physics terms are appearing together, more maybe bio data terms also appearing together in line with the grouping of documents, right? So the lines here are showing the strength of this group of words in these documents. There is a new feature here. We see we have a very strong group of words, top words, right? So the, of, a, to, in. These are in usual topic modeling practices. These are, people are asked to remove them, right? So, which in fact is something puzzling, because if you have a model that is supposed to capture the different frequency of words in different documents, I would expect these models to be flexible enough to be able to describe words that appear in all documents, maybe with a similar frequency, which is in fact what our model is doing, right? So we are just noticing that these words appear with a similar frequency in all document groups, and so we group them together, right? So they are grouped together. And interestingly enough, here some words that we could compute as stop words were not grouped together. There are maybe two groups. This is inferred from the data, right? So I think this is a positive property I would consider of this SPN. Right, so we have a more efficient compression of the data, no need to specify number of topics. The clustering of documents is done automatically, as I mentioned. And then we extended this also to the case where metadata and hyperlinks are present, right? So this is extended in line with stochastic block model approaches to multi-layer networks, right? So we consider now our bipartite network that we considered before. This would be one of the layers, but then we have an additional layer, maybe of the links between the documents, and then we add another layer of text, another bipartite layer, and we perform this SPM, multi-layer SPM, also introduced here by Thiago. And here is an example of another Wikipedia example. I'm showing the network here. It's a directed graph. The node colors here are the metadata, the tags that users gave to each Wikipedia page. And we got it from math, physics, and biology. And we see that the links here are not necessarily distinguishing between them. So if you use only the network, right? So if you do a community detection based on stochastic block models using only the network, no text, we get two communities, right? So which we see that physics is somehow split into half to the math, half to the biology. If we do if you use the hyperlinks and text, we do the topic modeling with hyperlinks, we get these four communities, right? So we still get a core biology, maybe a core math, but we get different clusters here. And in fact, looking at these clusters, they make sense, right? So we have here in this green cluster, we have things like protein structure prediction, X-ray crystallography that were previously linked into the biology. Oh no, by Wikipedia users, they were here at the border, right? So they were physics topics, but here they create a new category. No? Here is an example of the topics we obtain here, just to show that we can have these groups of words here as well. And yeah, if you want to interpret or look at what this topic means, and here are just as a smaller data set, is a project I'm working now with Professor Charlotte Schubert from Leipzig, with interest in ancient history, maybe an example from the humanities, as was discussed before. She's interested in texts from students of Socrates, Xenophon, and Plato. She gave me this corpora, and in an unsupervised way, we applied our methodology, and we see at the leaves of these three are all the documents. One layer before here, it's the cluster at the first level, and we see that we cluster them. So this is based only on text. Then we see a good cluster in between that separates the two authors, so they're not using this information. But apparently the cases where there are mixed clustering seem to have some plausible explanations, or some interesting explanations, at least according to Professor Schubert. I have there is a GitHub repository with the codes, and more recently I created a Google Colab. We could go through that, but check there that reduces the threshold to use this methodology, at least for small corpora, should be able to run in the Google Colab in the free version. And yes, I think that the interest here is now to see if this methodology is not only statistically better, which I think we demonstrated, but also if it can be useful for those using topic modeling and in digital humanities and other applications. Yeah. So let me just conclude this. So the SPM models that were proposed by the emerged in the community of statistical physics in complex networks, complex systems, for the problem of community detection in networks, a traditional problem nowadays in network science, can be easily adapted to the problem that is traditionally topic modeling and machine learning, computer science application to text analysis. So this is a fully non-parametric and can cluster the documents. It's based on the generative process. The underlying model is known, is the stochastic block model. And it's based on an inference of the parameters of this. We adapted this to a multi-layer setting, right? So, and here are the two papers we published on that. And if you would be interested to apply these, or if you are interested in applying these in your data set, I'm happy to please get in touch. Happy to discuss further. Yeah. So thank you. I'll stop here and take questions again. Yeah.
Yes, thank you very much. That's great. Highly inspiring, highly useful. So we got 12 minutes for discussion. Andres Karius has one. I also have one. Andres, go ahead.
Yeah, hi. Am I audible there?
Yeah, I can hear you. Yeah. Okay.
Okay. Right. So yeah, thanks. So I remember when this paper came out, it seemed like really interesting, and these triangular plots are rather convincing that this is a better model than LDA. But I tried to look it up, but I couldn't find it. But has there been any attempts to compare this to more modern models? Like there's now a whole literature about these sort of topic modeling based on pre-trained transformers like BERT and stuff like that.
We haven't done this, right? So I think the comparison here is meaningful, or can be mathematically done, statistically done, based on these equivalents between PLSI and SPMs, right? So I mean, and so we can. LDA is a generative process, right? So LDA is framed as an inference of parameters of a generative process of text. People don't see it as such, but it is. Right? So, well, if we go to transformers and pre-train, we are in a very different world, right? So I mean, it's
well, it's different. But I mean, the issue here is that both of these models, like the network and the LDA approach, they assume that words are just sort of units which are equidistant from one another. But if you have synonyms in one, two texts that basically talk about the same things but use synonyms, then these models would capture that really well. Whereas in pre-trained models, you already have the semantics of languages kind of built in, so they have been shown to perform better than these older ones. So that's why I was just curious.
No, I'm fully aware, and I understand the limitation of the bag of word assumptions and the impact of large language models in the world. So I mean, this is not something we are aiming here to reproduce or claim that we will be better than these models. The point, I think, the more general point make here is within a well-defined machine learning problem here of unsupervised text classification, right? So I mean, without this pre-trained access to this pre-trained, we can make contributions on a methodological level and based on our use of a formulation of the problem as an inference of parameters of a natural generative process, right? So that is in terms of in which extent and in which cases this is now beating state-of-the-art applications in natural language processing or in text analysis is something that I will not risk to evaluate in full extent. Yeah. But it is potentially interesting to compare in which settings to use that or not, right? But
thank you very much. I'm sort of glad I can ask my most favorite question, but in general, I think this issue here is what has just been discussed is a very important one, that oftentimes these kind of contributions are superimposed by developments that are then even more popular and stuff like that, but they turn out to be super important, right? So maybe topic modeling has been replaced with BERT and stuff like that, but this particular advance is a different kind of advance over sort of like having just a better method, because this method is more messy. Machine learning, we don't know what's going on, but here we know in this particular corner exactly what's going on. And so maybe explaining why BERT and all that kind of stuff works better has something to do with that, because it may be intertwined with it in sort of some unexplainable way. This is, I think, why we need more complexity science to explain better these kind of things that sort of like are non-intuitive in some sense. So here comes my favorite question, which if you could bring up the slide again where you had the bipartite graph with this edge bundling and the stop words. So whenever we come up with a method that is really good in cutting stuff into intuitively interesting pieces, or even quote unquote more correct pieces or buckets or whatever you mean, my favorite question is like, how about confusion? So there's always this other side. So you can actually sort of like have your, you know, squares or rectangles along the diagonal of a matrix, which ideally, you know, in modularity, if that's really high, they're all discrete. But then there's stuff happening off the diagonal. And that I don't understand if that is like sort of like fully, you know, the inverse, or if there's something else going on. But often what I know as like, if I put my art historian hat on, is confusion is where the interesting stuff is. Like, you know, it's one thing to say, okay, this is a Bruegel, this is a Rubens, but if it looks like half Rubens, half Bruegel, it becomes interesting. So how about that? Like, how about that flip side? How would, in a paper where you have this figure, in an imaginary textbook where the second paper that talks about confusion is like, how would that figure look like? And what would be the relation between the two? Or if we cannot answer it yet, then this is a good challenge for the future.
Yeah, so what I can say is that, for instance, if you feed into this stochastic block model approach, just random text without any structure, the outcome of this model will be that there is no structure. There is only one group. Okay, so we will not be finding patterns when there is no pattern. Okay, that is something that not all models are like that. Right? Not all methods are like that. Right? So in fact, most are not. And the second thing is that what we are looking here is the most plausible partition from the posterior point of view. We can sample from these partitions, and we can look at how plausible it is, different links and different relationships. So in principle, I think what you are referring to, we could try to quantify what are the most surprising aspects, what are the connections, and then try to highlight what are the documents that have the most unexpected mixture of topics and things like that. yes, we haven't done it, but from the stochastic block model point of view, this is all coming through. And,
so but you're saying we could have a kind of ensemble of partitions and sort of like look at that, at the stability of boundaries.
We will sample from the posterior of partitions according to the value of the posterior, and they will be giving different plausible separations of the words in groups and topics. And now, and back to the machine learning and large language models point, right? So I think that is the point, right? I mean, you highlighted better than I did. So, right, are we happy with these large language models where we don't know what they are doing? And chatting with them, right? So are we happy to live in this world where we rely on things only by their outputs and their outcomes, or would we like to understand what are the assumptions, what are the outputs based on, right? So and in this framework here, we, as you mentioned, we know why the models are doing what they are doing, and we can also modify them, so we can interpret them, right? So we can perform all the benefits that a proper statistical inference, proper model comparison can do. And that is the motivation to work on these models in generative processes, and to formulate data analysis as an inference of these generative processes, right? So which is not beating scores. No? So we are not playing that game.
Yeah, thank you very much. I think we reached the end of our 2-hour time slot. This was highly exciting. So this particular kind of play at the end, I think is sort of, you know, in the week before GPT-4 will be released. And the hype of these machine learning models will probably go on, what they can do and stuff like that. But as we go on, we will also learn what they cannot do. And then the pressure to understand what's going on is probably much, much higher. And their science in this kind of realm, or in this kind of way that you describe, becomes ever more important and interesting. In a similar way as during the pandemic, even the most qualitative humanist will figure out that quantification and computation sort of are unavoidable topics, and we need to understand them. And I think that is sort of something which I find supremely fascinating. The thread you weaved in as sort of a side thing, which is this description length topic, basically understanding as compression or understanding as comprehension, is a really interesting one, because if we are successful in doing that, we will use less energy to do the same things, which is important for climate change. So there's all these like fallout effects, like, you know, David Wolpert is working on the thermodynamics of computation, which is deeply intertwined with these kind of things. And so in some sense, one could say complexity science and natural science more general have the potential to really revolutionize the humanities in the same way we have revolutionized, you know, energy and agriculture in the 20th century. So this is a really, really exciting kind of way forward, even though it will be hard and interesting. And the question is, where will the money come from? And this is always a side thing people need to do once they have a physics professorship. Next week, we will actually talk again about words and word embeddings. We have Dustin Stoltz, Finding the Body and Sound in Word Embeddings. And one thing we are very keen on, not only disciplinary diversity, gender diversity, but also age and academic seniority diversity. So our next speaker will be a PhD student, which will be our youngest contributor, I guess, this semester. The week later, we will have Ana Clemente. So this whole semester is very sort of cultural evolution and complexity inspired. And let's thank Eduardo Altmann again. This was really, really great. And I hope there is more people who return to this on YouTube. I certainly will in the future. And so, yeah, in December, we all want to see you at the Cultural Data Analytics Conference, which will be announced. Thank you very much.
Thank you, everyone. Bye-bye.